Everybody, yes. Good morning, everybody. Welcome to the third day and the final keynote. Here today we have Dianni, who is currently the head of the market development at the European GNSS agency, where she's been working since 2009. Before joining the GSA, she worked in the private sector for more than 10 years, both in aerospace and information technology, gaining extensive experience in applications of space-based technologies for the transport sector. She holds a master's degree in aerospace engineering from the Politecnico di Milano and a master's in economics and business administration of government and nonprofit organizations from the University of Ferrara in Italy. And today she'll be presenting on satellite positioning, driving the emergence of new ITS applications. Let's welcome the speaker.
Thank you. So thank you for the introduction and thank you for the organizer for inviting me to this conference. Actually, as has been said, I'm an aerospace engineer. So for me, this is a good learning opportunities of computer science and other discipline that I don't really know. This morning, I didn't know if to be happy or not happy that it's raining. From one side, I'm happy, so at least few people made it to the conference, but I hope the weather will improve so we can enjoy all the afternoon we will have in front. So I'm guiding you today in this topic of satellite navigation to see what is the contribution it can give to connected ITS and especially to automated and autonomous vehicles. So I will go through three topics. The first one is what I said, so satellite navigation and the future trends in ITS. Then I will do a deep dive in autonomous vehicles. And finally, funding opportunities for innovation. My agency is a public agency of the Union, of the European Union, and is also a funding agency of research and development. So we have now two important opportunities open that I think are of interest of this community. So what about the trends and our vision? So as you may know, the history of satellite navigation is a recent history. If we think of the first, let's say, device for everybody that was not for the military or for the high professional, it was back in 99, so not one century ago, but not the full one. Then one of the big revolution we had in satellite navigation was TomTom, so the in-vehicle personal navigation device. And we are back to 10 years ago when it was introduced, and now they are almost disappeared, at least on the European market. So you see how also this technology is evolving quickly. And then the big revolution was in 2009, when the first smartphones that were including GNSS appeared on the market. And now it's common practice, so you almost don't find anymore a phone without the satellite navigation inside. So the question is what's next for our community and what could be the influence on ITS. So exactly we see that one of the few examples, so we don't have the magic sphere or the crystal ball, but connected vehicles and autonomous vehicles are for us the next revolution that will influence also our segment of satellite navigation. We see another trend that is the location-based payments. So more and more we pay things based on where we are. So we can use a certain digital right if we are in the proper place, for example. And finally, we see emerging a new supply chain monitoring concept that will see also the role of satellite navigation. So no more all the people are located in a sense, but also all the things. At European Union, we have some policies that are helping creating a momentum around satellite navigation. The first one is the emergency call. So in each vehicle from 2018, we will have a box that is able to locate the vehicle in case of accident and to send the emergency call. And a similar thing will happen on the trucks via the digital tachograph that monitor the time of driving and rest of a truck. And all these boxes will be embedded in the vehicle and will start also to be available for other services on board the vehicles. But when we say satellite navigation, we always quote this acronym, GNSS, the Global Satellite Navigation System, what it is. I used to say we are not alone. So in Europe, we are building our system, we will see. But also other regions are doing similar. So of course, we have the American GPS, that is the first one, is still there, is also under modernization. We have the Russian GLONASS that has been recently modernized. The Chinese are coming with the global satellite system. We have a regional system in Japan, QZSS, and the regional system coming up in China, in Korea, in Australia. So it's a global trend to contribute to this global satellite navigation system. And what it means for the users, it means to have more satellites available, also higher quality, because the new generation come, of course, with some new feature. We will see some of them. But what's the European contribution to this project, to this overall global project? So first of all, Europe has already a system that is up and running since 2009. It's called EGNOS. It's a so-called SBAS, so satellite-based augmentation system. In few words, it corrects some typical error of the GPS signal and give also reliability on the signal. The second pillar is Galileo, that is the worldwide navigation system that is currently under deployment. We have now 10 satellites launched, and it's all made in Europe. We have some good news from time to time, because Galileo is not known to have been the easier project of Europe. So we launched last week the satellite number 9 and number 10, and the launch was successful. So we have now 10 satellites in orbit. 2 additional ones are planned to be launched by the end of the year, in December. We maneuvered the 2 satellites that had an orbit anomaly during the launch, and now the recovery plan is under preparation, so they will be partially recovered. And we plan to start next year the launches with Ariane 5, that is the main European launcher that can bring 4 satellites per time, while now we are doing 2. So this will improve the deployment rate of the constellation. At our agency, we publish every year a market report. This market report gives for different application segments of satellite navigation an overview of what's going on. So the first message that we found also this year is that there is still a growing trend, quite a good one, in satellite navigation for the consumer markets and for the automotive market. So we still expect a huge growth till 2023. That is the year till when we forecast. And the driver are the mass market. So we still used to separate what we call LBS, so location-based services, the one that go on the smartphone, from road application. And together they make the most of the market. You see, it's 53% plus 38%. I already told my colleagues that I see that in the future, probably we cannot separate anymore. There will be a convergence of services on consumer devices that will serve all our mobility. And what about the technology? So first of all, in our report, we already have a clear trend that is happening, and this is what we call multi-constellation. So we analyzed the data of 300 receiver model, and we saw that multi-constellation, so meaning that we have inside the same chip the possibility to receive GPS, Galileo, GLONASS, Beidou, all the system available. It's becoming practically common even in consumer devices. And what's next? What are the main drivers in the receiver technology? So first of all, one driver that I think the automotive sector, but especially the connected vehicles and the automated vehicle sector should look at is the multiple frequency. So today, the chip that you have in your car or in your phone or in your iPad is working only on what L1, that is the frequency of GPS. GPS itself, Galileo and the other system are introducing other frequency. This will give much more accuracy and robustness to position. It's something that will come in the next years, probably in 2018, 2020, because the market will take some time and the technology to catch up. But the frequency will be available very soon, already from next year. So it's time to invest and research in it. The second one is the authentication. So currently the GNSS signals are not protected, so can be spoofed. So there could be attempt to spoof it. We see that now this has not been a real threat because actually they are most used in cooperative kind of applications, but more and more there are payment based on the position, more and more there are safety critical application based on the position. What we want to do in Galileo is to put a sort of digital signature on the signal so we can be sure it really comes from the satellites. And this feature will be available in the next 2 years. Then we see that GNSS, of course, is not alone. So there is, in the final position, we calculate the inclusion of other technologies. The most relevant for us is the signal of opportunity. So many radio signal used for the final positioning and the sensor fusion. And finally, we see in the future appearing very high accuracy services provided directly by the satellite. Is a centimeter level accuracy that today is available only for professional applications. So oil and gas companies who have to maneuver ships around platforms. We see that this may become available also for the more consumer markets, especially for autonomous vehicles. Galileo will contribute with its commercial service. So let me go quickly. What is our understanding of automated vehicles and how we see the role of GNSS? So the history of automated vehicles, of autonomous vehicles, is even older than our satellite navigation. It goes back to the late 70s. We analyzed a bit all the milestones that took us here today, and we saw that there were many steps, but still we are not there. In fact, we see for the future the 4 levels. So from what we can have today or in the next few years, so the level 1, so function-specific automation. Level 2, the combined function automation. Level 3, the limited self-driving automation. And finally, what we dream of here, the level 4, so the full self-driving automation. So the question is, how we will get there? And from our studies, it emerged that a self-driving automation will appear not before 2020, even if many steps will be done in the meantime. So what the autonomous vehicle will bring to the industry? So what is the impact also on us? So we see that the autonomous vehicle may trigger a big change in the industry. And to see the growth of software as value-added part of the car. So today, this is not the case. So the hardware part of the car is still the one with which we sell the car today. So we see that in the future there could be dedicated hardware makers, dedicated software makers, and vertically integrated experience makers who control all the aspects of the car. Also, we see that there is a big change in the attitude of the user. So the user are becoming more and more entities that use the content in the car. And this will bring new services and also new stream of revenues. So we see that there are the traditional players, so the OEM, that has the clear advantage to be familiar with the automobile, how they control the industry, and they know how to make a safe and good car. The challenge for them is to think out of the box, so to see this new revolution happening and to interpret it. We see the new entrants that has the advantages to be more risk-taking, less risk-averse, to be more innovative, but on the other side, they really don't know this world. So for them, the challenge will be to really understand how it works and to make it done. And what are the barriers that we see? So we'll not go through all of them, and there have been many presentations about the barriers here. But I want to underline some of them. The first one is that from technology and infrastructure point of view, we still see a lot of work to be done, especially in the software part. Then we have the part of the cost. So still the solution that we can use today drastically increase the cost of the vehicle. So we think that it's important to think of solutions that then can be really part of the market. So the question here is how we can go from level 1 to level 3. So you remember level 3 is the limited self-driving. So it's not still the dream, but already self-driving. And from what concerns the technology, we see that there are some key technologies that are in some way approached during this conference that has to be further developed, especially in the use we do in the software and the intelligence of the car, of them to get to the point of the self-driving. So our vision is that the solution will not be a sensor-based solution only, so a standalone vehicle with its sensor. It will not be only a connected vehicle. It will be the fusion, the converged solution of the two. And we see that the advantages of this will be to reduce the cost in terms of onboard sensors, so respect to the standalone solution. But we aim also to decrease the cost in terms of infrastructure. That's where we come in place with GNSS. We think that a good positioning, reliable, accurate, and possibly based as less as possible on external sensor and external infrastructure is essential, because we'll contribute not only to decrease the technological barrier, so giving a reliable positioning, but also to decrease the cost. That is one of the other barriers we see for the automated vehicle. So what are we doing to contribute to this? As I said, we have 2 funding opportunities open now that will materialize in project very soon. So the identified need that we have is that the GNSS chipset, that the one that are in our phone, are strongly driving the market, also the market of the GNSS chipset in the vehicles. So what is happening in concrete terms is that they call automotive receiver simply a consumer device that has been upgraded from the hardware point of view. But there is not a GNSS chipset, or there are few, that are designed exactly for this purpose, to serve the connected and autonomous vehicles. So there is the risk that the GNSS chipset industry will not design this dedicated product for autonomous and connected vehicle, because their interest and their drivers are in another market, and the numbers are completely different, are so big that they have no interest. And this will mean to lose, for example, some of the possibilities offered by the new GNSS and by the combination of them. There is, in our opinion, still some work to be done to get to a very good positioning. And this could save and could reduce the cost on board the vehicle. So our target is to create a reliable, very accurate, and possibly certified, we call it GNSS engine, because we think we should go beyond the receiver, the silicon part, but also the software and the algorithm around the silicon part. So we call it engine. So our dream is to have a certified engine, so both the car makers and the new entrants can make an informed choice of what they're putting in their vehicle and in their innovative solutions. For this, we open this new possibility. The first one is what we call eGNSS engine for safety critical application. And here we have clearly in mind connected vehicles and autonomous vehicle. So the budget is 4.5 million euros for one project. It's a grant, what we call a grant, so we fund 60%, and we ask to the participants to contribute in kind contribution or their contribution for the rest. So the overall budget is bigger. It's around 7 millions. The main objective is to develop the GNSS engine to exploit the differentiator of the new GNSS, and in particular of the European one in this case, and also to contribute to the standardization, so to see how this can bring to a certified GNSS engine. Who can apply? So the consortium must be formed by 3 entities that come at least from 2 different member states in the Union. So when we say entities, we mean industry, SME, and research institution, academia. As we see the ideal consortium, we see possibly an OEM or one of their main suppliers, so tier 1 or tier 2, a receiver manufacturer involved, and the research part of GNSS. It's open now. The deadline is 30 of October, so there is time to participate. And I invite the community here present to read the tender and to take advantage of it. We also open another one that is more addressed to what we call payment or liability critical application. So here we are not talking anymore of a native device in the car, but more of software that goes in onboard units or devices designed on purpose at the moment. Payment, so for example, all the mobility as a service concept, where we will not in the future pay based on the ownership of our vehicle, but how we use it, if we use it. And the liability, for example, this new regulated application we are putting in place, like the digital tachograph, where the position imply also enforcement or liability. So in this case, the funding envelope is 6 million euros that will be divided into projects, 3 million each. The funding is still 60%. So here we focus on developing the GNSS engine and exploit the differentiators. The rules are pretty much the same, apart that here we don't see the need for OEM or car maker to be in the consortium. It's more hardware and software developers and the research institution. The deadline is the same, so it's still open as well. So with this, I finish my speech, and I thank you for the attention, and I'm available for questions now or after during the break.
So I think we have some time for some questions. Are there any questions from the audience? Yes. Do we have a microphone? One moment.
Thank you. I'm Alwyn Hofman from Northwest University in South Africa. There's been a lot of focus on the required new capabilities to be built into vehicles. My question is, what about the requirement for more intelligent roadside infrastructure to communicate with vehicles and to provide better traffic management capabilities? I know in one of yesterday's keynote speeches, it was mentioned that if all vehicles should become autonomous now, that the traffic may be chaotic because we don't have the traffic management capabilities to properly handle them. So my question is, what is your views on the requirement for more intelligent roadside traffic management capabilities, and how should that interact with the new autonomous vehicles?
Okay. Thank you for the question. So as I was presenting maybe a bit quickly, our vision is that we will have a self-driving, at least the beginning phase, only with convergence of the two. So the part of the vehicle and the part of the infrastructure. So the connection with the infrastructure and the connection among vehicles. So only when there will be convergence of these two, we can have a acceptable self-driving. This is our vision. For what concern our part, so the part of positioning and satellite navigation, we had indeed 2 projects in our R&D program that were based, so one of the institution involved is here present today. So the concept there was that if you can communicate among vehicles and with the infrastructure, you can do what we call the relative positioning that permits to arrive to already now without additional sensor to lane level accuracy. So for us, it's essential to have also the infrastructure and the communication among vehicles available to have the level of requirements that that will permit the self-driving. And we're pushing the institution to go in this direction, even if not easy.
Any other questions? Oh, we have a couple more. We'll go to that.
Yeah, the positioning engine, that's really a good and nice idea, but it's for special application. Do you think it will reach also the consumer market later on?
Hey, sorry again.
So the positioning engine
Yeah.
is for some specialty, for some special applications, not yet for consumer application. And do you hope that in some time also consumer application will use this?
Yeah, that's a good point. So actually we see that, so we dream of it. So we dream to bring this innovation also in the consumer application. So meaning today the smartphone, tomorrow I don't know what will be the next device. However, we think that in the vehicle we have some advantages we should not forget about. For example, the power consumption is not so a key driver, while in the smartphone it is. And this is why, for example, the consumer devices are not taking advantage of this dual frequency that is clearly coming. So even triple frequency, but dual frequency will come very soon. But for them, the power consumption is such a driver that they even don't think about. While, for example, on the vehicle, we can do it. So our point is that it's a pity that we take, what is happening now is that we take GNSS chipset of the smartphone, we simply upgrade to automotive, and that's all. So that's why we want to create the engine. So we want something that can use all the potentialities, forgetting about the limitation of the consumer. So coming back to your questions, yes, in the future we will want to bring it, but we see that the playground, the place where we should do it first, also because the requirements are more strict, is in the vehicle, so in this field.
Great. Well, so I think we'll hold off on any other questions until after the break. So let's please thank the speaker one more time.
Thank you.
And so just real quickly, we have a little something for you to thank you for your talk.
Thank you.
Sorry.
Yeah, the picture. Ooh. It's heavy. Thank you. Okay, this.
Okay, so thank you, everybody. And now we will move on to the next part of the agenda. Oops, not that. Okay, so at the banquet the other night, we did have a presentation of our ITSC awards. So these are IEEE awards that are given by the society every single year. And if you're not aware of them, you can see up here, there are a number of awards that we give out. There's the IEEE ITS Institutional Lead Award, the Outstanding Research Award, Outstanding Application Award, and of course, our Best Dissertation Awards that we're very proud of. So what we're gonna do in this particular session is we're gonna have some of the award winners for this year give a chance to talk about why they were given the award. And I'd like to encourage all of you to keep your eyes and ears open as we do this every single year, and we'd like to have lots of you present your work for consideration. So if we go here. So the first award that we have today is the ITS Institutional Lead Award, and that's for LISA, the Laboratory for Intelligent and Safe Automobiles, and the director is Mohan Trivedi at the University of California, San Diego. Okay. We had the Outstanding Research Award, which was given to Umit Ozguner from The Ohio State University, who is now going to be the editor-in-chief for the new intelligent vehicles transactions. Unfortunately, he's not here today and won't be able to present. The Outstanding Application was ACP-based Qingdao Parallel Urban Traffic Management and Control System, which was a very large team headed by Professor Fei Yuang and the PTMS team. We had 3 Best Dissertation Awards. The third prize was Modeling of Driver Behavior in Real World Scenarios Using Multiple Non-Invasive Sensors by Nanqing Li from UT Dallas, who's now working at Honda Research Institute in Mountain View. Second prize was from Meng Wang, Generic Model Predictive Control Framework for Advanced Driver Assistance Systems from TU Delft. And our first prize winner this year was Traffic Modeling, Estimation, and Control for Large-Scale Congested Urban Networks. And this is Motion Galloni from EPFL. So before we get to the talks, I just wanted to give a round of applause for all these people so we can recognize their hard work. And so what we'll do now is we'll start off with the program, and if I can ask Professor Trivedi to come on up. We'll start with the Institutional Lead Award. So give me some kind of an indication to start 5 minutes before. I also need audio for this one here. Sorry. Yes.
Oh, thank you, sir. I may have to change the resolution. Let's see here. Wonderful. Thank you so much for this opportunity. I do want to start off by really expressing on behalf of my team a grateful thanks to the IEEE ITS Society, its awards committee, and colleagues in large to give us this extremely special recognition. It really means a lot to lots of young scholars who have been associated with these efforts for at least 15 years. Having said that, I also wanted to share with you in this 15-20 minutes we have a glimpse of a journey that our team has taken about for the over the last 15 years. And if I had to just find one title to describe that, then I might say that this is really a vision, and I'm playing with that word, vision meaning computer vision for sure, but it's also something which is something that our team would like to aspire for, and I have a feeling that as a community, we also want to aspire for intelligent and safe vehicles. So very first thing that I may give you a feel for is I have divided or attempted to divide this into few key segments. And I really do not consider this to be some kind of a plenary presentation, but it's more of a trigger for a conversation that we as a community can have today, later on, and continue to have. But basically, it deals with this thing that when we talk about intelligent automobiles, what does it mean? Does it mean autonomous, self-driving robots, or it means something else? It is also something that we need to cogitate, that if we come up with these self-driving autonomous robots as the wagons we will use in the future, what is the role of humans? Are they going to be just involved in writing you a check when you go out buying it, or they might be even interested in sitting in it and having fun while that is being happening, and certainly being safe? When we do that, it turns out that we may have to actually think about a paradigm where this new type of mode of transportation we are talking about may really be a team effort where intelligent systems, either artificial or biological, they don't go there competing with one another, but really go in there to cooperate with one another, knowing full well that there are certain shortcomings that each one has, and also there are some strengths that we might be able to use. But how do we come up with a setup where we don't go there and it is either a robot or a human, but it is really something which is like a distributed cognitive system, where intelligence of this distributed cognitive system is at a higher level than anything that an artificial robotic system can accomplish or a smartest of the human drivers can have. And in between, as time permits, I might also give you some illustrations of few things that we have done. But so let's talk about the beginnings and the team. So as you recognize that, I mean, this is something which is clearly an effort of lots and lots of very bright scholars, young scholars, who have started doing their work in our lab, but have continued to pursue some of these efforts even beyond graduations. And case in point would be the chair of the session here, Professor Morris, who also at one time used to sport his long hair and sit in the center of the group picture. And then there are others also, almost all of them have gone on to pursue things which are related to development of intelligent systems. And then we can talk about individuals, and I will never stop talking if I talk about our students. But in any case, there were also very good bunch of collaborative colleagues. Few people who really influenced our earlier thinking are people who are not from engineering, but they are from cognitive science and computational sciences. But these are the people who are pioneers in the field of distributed cognition, especially Ed Hutchins and Jim Holland, who are also faculty members at UC San Diego. One of our dear colleagues, Professor Bhaskar Rao, he is an expert in digital signal processing and machine learning, and other people from the group, in the community that we have been fortunate to be part of. And as it happens with any work that you do of this kind of long history and continuity, we were again very fortunate to have had a great bunch of sponsors who I really think of them as partners from government as well as industrial corporations. So just to trigger this thought about what self-driving autonomous robotic systems are, we must recognize that really wagons, which are horseless, were not there until about 130, 140 years ago. So it's a relatively short history of automobiles. And just after, say, 40, 50 years of its adaptation, people started thinking about robotic systems which would drive on the highways safely when you and your family can be playing Scrabbles or game of chess or whatever. And this was something which appeared in the middle 50s, 1956. Popular Science did a special issue on things which were basically this. And they, as you look at it, I mean, they're basically making a rail track by instrumenting vehicles and having these things go forward without any collisions or any stress on you. Another 50, 60 years go by, and this is the latest concept drawing that is presented by some of our colleagues from Mercedes, and they show something which is significantly similar, at least in the looks of it, to what people in the 1950s were thinking about. And so this is really something that we all as a humanity would aspire for. But when we do that, I mean, we have also scientific, very careful engineers and all that. So we really like to build systems and prove our point that these things really are feasible, practical, and something that you can scale up, hopefully. So periodically, and now with quite heavy frequency, there are efforts which are really eye-popping demonstrations all over the world where people have developed these self-driving systems. But when we look at it a little bit carefully, even them who are showing these ones, they are not really abandoning research by saying that, oh, this demonstration is going to be something that everybody will be able to use. But actually the research components of all of those things is also expanding very rapidly. And why is that? I believe that whenever there is research, that means there are some problems to be solved. So we need to be having some kind of a feel for where the problems are. So one of the things that we can see that after looking at these self-driving vehicles and all that, we need to ask a question that will you have humans who are going to be willing to let go their control in these robotic systems or not? At the same time, there might be some other issues which I know many of you who are in the business of selling cars are thinking about that. How are we going to market these things? Would there be at least a minimum number of dollars that people will have to spend in order to get this? Would there be some kind of a performance requirement which would say that if I have this, I'm going to be going faster than everybody else or safer than everybody else or whatever it is? But what are those metrics? And this one that people were not talking about until a year ago or so, probably in open and loud. But the question needs to be asked is that what is the tolerance that you have about the accidents that you are going to permit with these autonomous self-driving robots? Because anybody who is going to tell you that there will be no accidents, they are not really telling the truth. And until 6 months ago, that was something that we didn't hear much about. But the question here is that the robot may decide that in order for us to meet the cost, the speed, and the safety constraints that they need to promote, robot cannot let go the control. Only then you are going to have the acceptable things. So now there is a conflict. What happens if the human doesn't let go, and what happens if the robot doesn't let go? One way to look at it is the conflict that happily married people have when they are driving together. My spouse never likes the lane in which I drive, the speed at which I drive, and I also vice versa don't like that. And that is, it takes a lot of experience to negotiate that thing over years, but robots are not going to give us that kind of time. So again, just to emphasize this point, that we were not talking about these numbers before, but our friends at Google had to face up to this, because now there are people like lawyers and insurance companies in the United States who will not let you go, no matter how big of your industrial budget would be. But the whole point was that now there are actual numbers where people are talking that when you drive this thing, we have had accidents. And your lawyer and their lawyer will argue. There is a whole industry of that in the United States. Whose fault was it? According to press release from Google, the fault was every time other vehicles. But I'm pretty sure there is a smart lawyer somewhere in Los Angeles who is going to prove them wrong. Okay? So if that is the case, where we are going to have a thing which is going to have conflicts, then what is the way in which we can at least make an effort to develop these safer, intelligent, stress-free types of driving mechanisms? So there is a premise that we have been talking about, and that is that we really love these robotic systems. That's the only thing we have done in our group over so many decades. But as we do that, we are also recognizing certain limits of artificially intelligent systems. And we are also observing how intelligent systems, and like us, develop higher and higher level of intelligence. And it is recognized that one of the key things about us exhibiting intelligence is our ability to understand behaviors, intents, actions of other people in our communities. If I develop myself to be an extremely intelligent person, but who is completely stupid in understanding the guy who is showing me different types of finger symbols, I'm going to be a failure in operating in a good social environment. But if I understand that, you will be, or the other gentleman or lady would be also gaining a better level of intelligence, and so would I. So we do recognize that at least the intelligence system that we represent, we have a capability to understand other things. And we are going to propose that the robotic systems, which are the self-driving vehicles, in order for them to increase their level of intelligence, maybe they should also come up with ability to understand the behavior of other agents, which are humans who are there. And so these people will have to know that, and by knowing that, it is not going to be really we have to figure out that it's not going to be deadlock, but it is going to be really a virtuous cycle where by doing this thing, our intelligence as a team would be more than intelligence of one entity. And that's basically what is driving the work at LISA. And to do that, I think one of the key things that we embraced in 2001 was that we went in with a thought that in order for doing this kind of systems, we need to understand not only what is going on around the vehicle, or not only understanding exactly what is the dynamics of the vehicle, but also understanding simultaneously whatever is going on inside the vehicles. And that kind of an approach has paid lots of dividends to us. But basically, we came up with an agenda, and this slide was made in 2001 when we started a large project, and I have not changed a word of it. I was just ignorant enough to say that this is something that we could accomplish in 5 years. In that team, it's been 15, and the journey continues. But the whole idea was that there are certain things that engineers and computer scientists can solve, but then there are certain things which really require us to think about intelligence, cognitive science, and psychology type of issues if we are going to have ability to understand what humans are demanding in the interactions and the understanding of the other agents. And it is not just the humans who are inside the car, but humans who are going to be around us also. So this has been the agenda for us, and then we have been developing things, and I need to walk you through some of the things, but let me just give you illustrations of few things that we were able to accomplish. So again, as I said, that we started with one vehicle, which was a project with Nissan and the state of California's sponsorship, where we instrumented these vehicles, and we really didn't know how to come up with machine vision or machine learning algorithms to analyze that data, but we started collecting this data, and that data is now multiplied by thousands of time, in fact. And there are 5 vehicles that we are operating even now, all developed at different stages with different types of sensors. But the idea is still the same, where we are saying that can we actually come up with a machine learning based paradigm, whereby observing how human beings, large number of them, drive their vehicles without causing accidents, can we learn the patterns which are associated with their intentions to do some safe maneuver, their intentions to either change or not change the course of the journey. And we developed several things. Some of them were associated with lanes, some of them were associated with brakes, some of them are associated with turns. And I'm very happy to say that the wonderful collaborations that we had with our partners, now there are versions of this one, especially in Asia and in Europe, which are now becoming part of commercial systems that you and I can go and buy. One of the things that people generally talk about, that you might be able to do these things, but are these things generalizable or not? So a few years ago, we got a phone call from Discovery Channel, that is a channel that shows some of the interesting things happening elsewhere. And then they said that they wanted to come and shoot some of the footage in our lab. But we have a rule that unless you are a UCSD employee or student, we would not allow you to drive this. So a few days before he was supposed to come, the team was supposed to come, we told them that you can come and shoot the thing. But he said, no, the whole setup of our show is that I need to be doing something. And I called our university lawyers. They said no. But within a couple of days, they came up with a $10 million one-day insurance policy, and we let them drive. But the interesting part was, and Dr. Morris was actually the caretaker of this operation a few years ago in our lab, but this person, who is the host of that show, was never seen by us or our cars, and we were able to read his mind 2 seconds before he decided to do certain maneuver. So generalization is possible, and that was useful for people to start building few things. And this is the one that I kind of put a question mark, but the whole idea is that as we are seeing this intelligent vehicles and robotic systems evolve, the sensors which are on the bottom half of those things are commonplace. That, I mean, they may change the brand, but there are lasers and lidars and radars and cameras, and people have been collecting data, and people have been developing fantastic algorithms for keeping yourself on the road and not colliding with other things. But what they haven't had in the past too much of, but now it is also fortunately increasing a lot, is the types of things that we have been collecting from looking inside the vehicles, also in synchrony with everything else. And this particular vehicle we have had the good fortune to run for the last 5 years or so. And there was a copy of that which was built by Volkswagen and Audi in San Francisco. And having seen what it was able to do, they have now allowed us to tell everybody that Audi A8 in 2017 would have these features, and basically that kind of a suite of cameras or sensors.
Autonomous or self-driving cars. The engineers centering around autonomous or self-driving cars, the engineers at Audi were in San Francisco today to show off technology that's a bit more realistic.
The whole aim of this from the beginning was to really work on technologies that would take the stress and the trauma and driving in very congested, chaotic situations and the wasted time and all that out of the picture.
And while the car has sensors that monitor traffic outside, it's also keeping an eye on the driver inside. 2 cameras are watching the driver, and if he takes his eyes off the road and begins swerving or an obstacle pops up, the car will take over control of steering and braking and even momentarily disable the accelerator. It's not exactly hands-free driving, more like having a really smart backseat driver.
Just like autopilot in a plane, the plane is often flown by the computer, but the pilot isn't in the back having a cocktail. The pilot's in the seat and needs to monitor it.
So I would not take too much more time here, but the whole point was that these things are now becoming practical, and we haven't stopped working with this company and few others to think about few other things that we can also add. But to conclude, I need to bring up my last slide here, if I can. So the whole conversation is about really these kinds of distributed cognitive systems where we are going to have human-centric, intelligent and safe vehicles. To do that, I think now there is a significant global emphasis on developing new ideas. We certainly are pursuing this and pursuing it with much more speed than what we have done in the last 15 years. And then we are also realizing, and thanks to my dear friend, Professor Christoph Stiller's initiative 6 years ago, where he recognized that in order for people to be convinced of the utility of your algorithms and your systems, it is important to do extremely careful evaluations. And evaluation, each one of us can do it on our own data, but that's not going to really increase the confidence of the community. So it would be wonderful that we have some bright student teams like Andreas Geiger did at Kitty and developed a database which is really one of a kind. And now you cannot write a paper on vehicle detections and all that without doing some kind of a benchmark with that. We got inspired by that, and in the last 10 years or so, we have whatever we are collecting. Now we are putting things which are mainly focused on looking inside, or things that are not in the kitty, things like traffic lights and traffic signs. And that one we are actually allowing anybody to access. And we have created in CVPR this year and in IV challenge where you can submit your results and see how your performance works out in comparison with others. So we have certainly had lots of fun having this journey over the last 15 years. I know that many of you are also on such journeys, and I would like to wish you all bon voyage. Thank you.
Okay, we maybe have time for just one question, if anybody has. No? Okay, in that case, let's just thank Professor Trivedi, and we'll move on. The next speaker is our second place dissertation award winner, Meng Wang from TU Delft.
Thank you. Thank you, Mr. Chairman. Good morning, everyone. I'm quite honored to be here to give a presentation about my PhD research. Well, I did my PhD at TU Delft and the supervision of linear diamond, surgical window, and the butterfly arm. Well, the title of my presentation is exactly the title of my thesis. But perhaps you will not got no clue what I did based on the title because it's really general. So I'm going to change the title to Controller Design for Autonomous and Cooperative Driving Systems. And what I did is to design those controllers and then assess their collective impact on dynamic traffic flow characteristics. Well, to start, I would like to, what are advanced driver assistance systems? Well, those are partially automated driving systems that support the drivers in performing certain driving tasks, such as car following and lane changing. And there are different definitions of autonomous systems, but for the sake of presentation, let's here define those systems into two categories of autonomous systems and cooperative systems. For autonomous systems, we refer to systems that only rely on their onboard sensors. There's no communication with other vehicles. And there's no cooperation, no consensus in the decision-making process. Their cooperative counterpart, however, exchange information via inter-vehicle communications with their peer cooperative vehicles. They even talk to the infrastructure via vehicle-to-infrastructure communications. There is also coordination and cooperation in the decision-making process. So I had a civil engineering background, so I'm really curious about the question whether those systems are relevant for traffic management. So the answer is, of course, yes, because ADAS change the individual driving behavior. So they change our gap and speed choices, change our acceleration and deceleration profiles, and this consequently impacted our travel time, our risk of collisions, and driving comfort, of course. And these individual changes will be aggregated at the collective traffic flow level, thus impacts the roadway capacity and traffic system stability. And as a secondary effect of these changes, the fuel consumption and emission in the road traffic systems will also be changed. So in a way, it is really important to design the ADAS systems to improve collective traffic flow dynamics. So what I aim at for the PhD research is to find a flexible design approach. So the motivation is that there are many control approaches available, how determine ACC and the CECC accelerations based on simple linear feedback control laws. Well, those approaches often miss certain features which are actually desirable. So for instance, in most of these approaches, there's no explicit optimization. And it could not address multiple objectives of safety, efficiency, driving comfort, and the fuel consumption and emissions. And there is no anticipation for the future in the driving context because there's no prediction in those feedback control laws. And it is not straightforward to integrate those approaches within the current traffic management architecture. So the objective is to develop a generic multi-objective control approach based on model predictive control, and while being fast and robust enough for real-time applications. So this diagram shows the workings of this framework. So let's consider a local traffic system, let's say about 200 meters in front of the controlled vehicle. Well, the state of the local traffic system can be detected by onboard sensors. It can also be detected by sensors located on surrounding vehicles or even at the infrastructure, then transmitted back to the onboard system via vehicle-to-vehicle and vehicle-to-infrastructure communications. With all the information available, the onboard system can make an estimate on the current traffic, on the current state, and then predict its future evolution. Well, by prediction, we mean predict the dynamic behavior of the controlled vehicle using a system dynamic model, and also predict the surrounding vehicles using heuristics or human driver model. So when you can predict the future evolution, then you can calculate some cost that addressing some undesirable situations, and those costs can be classified into different categories, reflecting safety, efficiency, comfort, and fuel consumption, for instance. Here again, we distinguish autonomous or non-cooperative systems with cooperative systems. For autonomous vehicles, we say they are selfish in the sense that they only optimize their own cost. While for cooperative vehicles, they cooperate together to jointly optimize the cost of the whole platoon. So if you solve this mathematical program, and then you can generate a reference signal. In this case, we consider the longitudinal dimension, which is acceleration. And the lower level vehicle controllers and actuators can execute the reference control signal. And as the vehicle maneuvers, the local traffic system changes, and the system goes to the next control cycle. So I'll skip the mathematical formulations and directly go to some examples. So we have worked out, we have designed actually several controllers in my thesis. And the first one is a multi-objective ACC, adaptive cruise control system. Well, this system, basically regulates the in the current ACC system, it regulates the speed and the distance gap with respect to your preceding vehicle according to the driver preference. While our ACC system, first is to maximize safety. This is achieved by penalizing the situation when you approach the preceding vehicle with a higher speed at smaller gaps. And it also maximizes efficiency in a sense by penalizing your deviation from your desired speed or your desired distance. And it's also maximized comfort. This is achieved by penalizing large acceleration and the brakings. And the feature is that it operates in full speed range, and it also has a collision avoidance mechanism in the controller. It anticipates the leader behavior based on constant acceleration or constant speed heuristics. It assume it's driving at the same speed within the predicted horizon, but this heuristic is corrected with the most updated information available from onboard sensors. Well, you can extend the ACC towards the so-called ecological ACC, which also minimize fuel consumption and emissions, in addition to the objectives of ACC systems. Under the eco-driving concept, you can also straightforwardly extend to platooning, so to design and CACC, a cooperative ACC system. So in these systems, cooperative vehicles coordinate their behavior to maximize safety, efficiency, and comfort for all cooperative vehicles. Well, this entails the cooperative vehicles exchange their state and control information via inter-vehicle communications. Well, the unique thing for this framework is that the cooperative control concept is not restricted to cooperation between equipped vehicles. Well, even a cooperative vehicle is followed by a human-driven vehicle and is following another human-driven vehicle. The cooperative control concept can still be applied. So the key is you need to predict the behavior of the follower using a car following model. And then this prediction needs not to be perfect. And in this case, actually no inter-vehicle communication is needed, and it can function at a very low penetration rate. So as I mentioned before, we are really we're really curious about the collective impact on traffic flow. So here is an example. What we did here is to, in a single lane simulation for homogeneous ACC and eco-ACC vehicles, and we generate disturbance to the homogeneous platoon, and then we plot the so-called fundamental diagram in traffic flow, which actually displays the relation between traffic density in the unit of vehicle per kilometers against the traffic flow in the unit of vehicle per hour per lane. So what we see is that for the ACC systems, that's in the red dots, this displays a triangular fundamental diagram, which is similar to human-driven traffic flow. And while the eco-ACC displays quite a different shape of the fundamental diagram, this entails the capacity and the critical density, which distinguishes the free flow to the congestion, is quite different depending on the system. So we are also in the control framework for certain formulation, you can also derive analytically the traffic flow stability criteria for homogeneous vehicle platoons. So this is called the string stability criteria, if you know this concept. So this is actually the only equation I put in the thesis, although it looks nasty, but it's actually quite powerful. It can predict which controller parameter setting the stability property, the string stability property of the certain controller parameter setting. And if you see this region, if you parameterize this one of the controller parameter, you lead to string stable region. And furthermore, for those unstable regions, we also distinguish in which direction the disturbance can travel in space and time. For instance, this is CU, what we call the convective upstream instability region. If you have a disturbance at the initial condition, this is let's display this with the driving direction from top to bottom. And this disturbance will travel upstream, that is against the driving direction. So this is also observed by the human-driven traffic flow nowadays. But if you parameterize UACC in this region, you get absolute instability region, which means that if you have initial disturbance here, that the disturbance will travel both with the course of time in both in the driving direction and against the driving direction. So what we call here the absolute instability, this has never been observed in human-driven traffic flow. So if you have a system in this region, you have really a new traffic flow phenomena that has never been observed before. So so far, so simple, because we assume homogeneous traffic composition, single lane, 100% penetration rate. We are also interested in mixed traffic flow features. So here we show an example of two-lane motorway simulation of 14 kilometers, while there are more than 500 vehicles simultaneously simulated each time step. Well, in the case of model predictive control for ACC and CCC systems, this is a complex networked control problem. So we also developed a distributed MPC algorithm for CCC systems. We generate temporal bottleneck as part of the motorway, and by lowering the speed limits from 120 kilometers per hour to 50 kilometers per hour for about 2 minutes, and then when the demand or the inflow from the origin is very high, this bottleneck can generate a traffic jam that moving against the driving direction. And what we call in the traffic flow community is moving jam, or stop and go waves, or ghost jams. So we examine different penetration rate of ACC and the CCC vehicles. And here are some of the results of the different penetration rate of ACC systems. So what I display here is still the space and time contour plots of traffic flow and the traffic speed in the considered road stretch. And if you see the speed contour plot, And this is driving direction. This is the temporary bottleneck, and after the bottleneck, we see a congestion that is moving against the driving direction. And as the outflow from the congestion is lower than the inflow into the congestion, the size of the jam increases. Well, with careful design and tuning of the ACC system, we generate a traffic flow characteristic that is much better. So we still see after the bottleneck, we still see congestion that are moving backwards against the driving direction. But now, due to the higher outflow out of the congestion, the size of the jam is much smaller than the reference case without any ACC systems. And with 100% of ACC, the jam still propagated against the driving direction, but it dissolved itself after propagating for about 20 minutes. So if we look at the impacts of cooperative ACC systems, the effects are more pronounced. So what we see here is that with only 10, this is still the reference case with 0% of CECC vehicles, and with 10% of CECC vehicles, we observe a small backward propagation wave, but this wave already dissolved itself at some 10%. And at this strength of bottleneck, with 100% of CECC vehicles, this bottleneck does not lead to a traffic jam. So these are some examples that we show to show the dynamic feature. And we are also curious about how we can integrate the vehicle platoon level controllers with the traffic management systems. So we also have a proof of concept study. So try to connect a variable speed limit controller at the link level, and with ACC controller at the vehicle level. So the idea is that the variable speed limits controller get information from road-based sensors and display the variable speed limits on the roadside gantries. And these gantries have vehicle-to infrastructure communication units, and it transmits speed limits to the ACC controllers. And the ACC controller use the variable speed limits at their new control parameter, and then locally still optimize their individual behavior. So we give some indicators here in this table. So this is those scenarios without connection to the variable speed limit controller, and those following three scenarios are those connected to the variable speed limits controller. So what we see is all the detected jams are resolved, and the total time spent in the network, which reflects the traffic efficiency of the road network, is lower than those without the connection to the variable speed limits. So we also see that the speed limits error in the space and time, which reflects the control effort, let's say, also decreases with the increase of the penetration rate of ACC systems. So to summarize, we did develop a generic control design methodology that can be applied to a variety of ADAS applications. We developed implementable algorithms for ACC and CECC controllers. We examined the impacts of those systems on traffic flow and found that it has a great impact on the formation and propagation of moving jams. And the proposed system can mitigate the congestion compared to the human-driven vehicles, and the connected variable speed limits control with the ACC can bring extra benefits. But it, of course, is never the end of the story. So there are more practical issues of delay and noise in the loop that should be accounted. And there are we focus on the longitudinal control in my thesis, but it's more complex to go to lateral control about cooperative merging and the lane changing. We did some work there already. Human factors is very important. The driver's role in the future should be clarified. It's a supervisor, it's how and when it should resume control. And there are some safety concerns during the authority transition. And the impact assessment, there are many studies using microscopic traffic simulations, but are they capable of doing the job? I mean, there's no sensors, actuators, or communication units in microscopic simulation models. And the cooperative traffic management in the era of vehicle, intelligent vehicles, so do we need to refine or even redesign current traffic management systems? And this is the last slide. I would like to take this opportunity to thank ITS Society, thanks Award Committee, thanks Organization Committee of the conference, thanks my supervisors, of course, and also my family, particularly my wife. Thank you for your attention.
Okay, so maybe we can take some questions if there are any from the audience as we set up the next award. No questions.
Okay.
Okay, great. So
Yeah.
we'll move right on to the next one.
Yeah.
Thank you. The next up, we have Mohsen Ramazani, and he will be giving his Best PhD Dissertation Award presentation. He's from EPFL, and I'll let him introduce his topic.
Thank you. Okay, sure. Good morning, everybody. I'm Mohsen Ramazani. I did my PhD in EPFL, École Polytechnique Fédérale de Lausanne in Switzerland. Now I'm just recently started as a lecturer in Monash University, Melbourne, Australia. So I flew a lot to come here. So my thesis is traffic modeling, estimation, and control for larger scale congested urban networks. The supervisor was Professor Nicholas Geroliminis, and the jury was Professor Takahama, Colin Jones, Jorge Laval, and Marcos Papagiorgio. So before beginning, I would like to thank my supervisor and Jack Haddad, which was a postdoc during that time at EPFL. Now he's an assistant professor in Technion, Israel. And this is a typical day at our laboratory working on MATLAB and also watching football Euro 2012. So I'm not sure about the results, but anyway. So transportation, is a need in humanly, and because of the urbanization, there is the traffic congestion, which dates back many years ago. So my research targets to operate traffic in a way that was not possible until recently, and by that the cities are growing in such a way that providing us with new technologies to operate and progress the management of traffic by combining different and multidisciplinary knowledges like control systems, applied mathematics, and physics, by exploring into big mobility data to gather some new patterns of mobility for modeling, and at the end, coordinated management of the traffic system. So I would like to start with the monitoring at the beginning, and then we'll shift to the modeling and management of the traffic systems. So big mobility data provides a unique laboratory for us to examine the complex patterns of mobility within transportation networks. But just by having that data, which is abundant nowadays, it's not enough for us to integrate different source of data and utilizing that data to infer some common state estimation for to analyze the situation of the system for modeling and control purposes. And our resolution was to integrate some advanced data mining techniques plus the knowledge from the traffic flow theory to combine together and bring in some new resolutions for us to analyze the system. So the first instance that we analyzed was a work that in the context of urban systems, if you have the traffic flow, and this is a time space diagram, and the blue lines are the trajectory of the vehicles. So the black lines is a famous phenomena in transportation, which is the shock waves that represent the discontinuity of the traffic state in time space domain. And by capturing these shock waves, which are very unpredictable, we can get many information from the system, such as the traffic delay, queue size. Basically, they provide a very wide range of information for the system. But we are moving into the new direction of the crowdsourcing with the recent deployment and increase of deployment in the GPS data, Bluetooth data, Wi-Fi data. So we consider that some of the vehicles are equipped with GPS data or Wi-Fi or Bluetooth, so they are moving, their sensors that are moving with the traffic flow that provide us their location and their speed. And our goal is to estimate these shock waves. So the problem becomes that from just a sample of the background, the physical phenomena, we want to estimate what is happening in a larger scale traffic situation. So by combining lots of clustering and classification methods and least square optimization, we can extend the problem to arterial. So as you can see, there are four intersections, and you can see these Q profiles, Q shock waves that we compare with different rate of penetration, error measurements in GPS data, and we also compare with the state of the art. We get much better results for estimating the traffic condition in urban congested arterials. Also, I would like to say that with Bayesian inference, we can also capture the probability of having a spillback, which is a very hard phenomenon to observe in urban systems. As you can see, for example, this one has 96% of chance for a spillback. As you can see, the Q spillbacks to the upstream intersection. So the second instance of the monitoring application of my thesis was travel time variability, which is a very hot topic nowadays because we are shifting from just providing one single index of the travel time to providing a distribution or range of travel time for users. And our goal was to shift from link travel time to route travel time, basically because our trips within an urban network consist of many links, so it's from point A to point B, and also provide a distribution, a non-parametric distribution. More importantly, we also try to capture the correlation of the traffic states within the successive links, and based on real data, we could incorporate the information into a Markov chain process to capture this correlation. And we test that with the NG SimField data. As you can see, this is the probability, and this is the travel time. The ground truth is the black diagram, while our estimation can capture well both peaks of the distribution. As you can see here as well, single statistics like mean or variance cannot provide the full information of this distribution, and we need to shift our way of thinking from just providing one single value for a travel time to providing the travel time variability for the users. So let's shift a little bit from the monitoring to the modeling and control part, which is basically my focus was the larger scale modeling and control. So congestion in urban system, because of the extent of the transportation system, is nowadays fragmented. And there is not enough coordination tools between the different jurisdictions of, for example, freeway and urban systems. And I don't think that I need to talk about why we are gathering here. Probably there is congestion out there, and our potential resolution was to propose a hierarchical system of system control approach. So I would like to show you this movie, which probably most of you have seen in the YouTube, but I would like to show that because this is the essence of my control contribution. So imagine a funnel that there is a bottleneck over there, so it can be like a tunnel or bridge or a traffic light, and in the rush hour, when every passenger, so there are lots of grains that wants to go from their origin to destination, there will be queue. So in the next experiment, the guy just tried to control the input at the beginning of the system, and as you can see, there is no congestion at this bottleneck, and it will empty the system much faster. So we can compare both of them at the same time as well. So we would like to be the smart guy that are controlling and creating artificial queues at somewhere else such that the performance of the system increases much better. To do that, first we need to have a larger scale urban traffic modeling. And the mental diagram, MFD. So recently there are some analysis on the downtown Yokohama based on real data that if we aggregate over time and space the information of a subregion, an urban subregion, we might get a very well-defined relationship between average occupancy and average flow. And the optimum would be to operate the system at here to maximize the average flow so that everybody can reach their destination faster. But MFD is not a universal law. And my goal was that to somehow manage the control systems to provide a well-defined MFD. And one other solution is the partitioning that, for example, in the downtown San Francisco, as you can see, the distribution of congestion is not very homogeneous, but by partitioning tools, we can find a sub-region that is more homogeneous that will yield to a well-defined MFD. So in abstract, let's imagine that we have a city, that there is uneven congestion. We have a CBD and the suburbs around that. So region 1 and region 2, and in abstract way, in schematic way, we have 2 regions. And our goal, which is this paper was one of the pioneer of the perimeter flow control, was that to introduce a set of signals on the boundary of the CBD or the region that we want to protect. So it's a set of signals, and we are only controlling these signals on the boundary. We don't care about what is happening inside the city. So our goal was to control the inter-transfer flow from the suburbs to the city center and vice versa. So there are 2 controllers operating on the border. And the objective is to minimize the whole system. And by solving the problem, by using model predictive control, we can stabilize the accumulation of the system to some to the maximum of the MFD, and on average, for this specific example, we could get 5.5 million average saving per trip. But that was just the cornerstone and the beginning of the building a hierarchical system of system control design for a network. So the next step was that not only there is an urban system, there is also a freeway going through the urban system. So now we have 2 entities, and this is the coordination that we are aiming for. So basically, the idea was to provide a coordinated control for the mixed urban and freeway network to minimize again, the whole network performance. And there we also have the perimeter control and also ramp metering. So 2 entities, 2 different control approaches. And it's getting more convolved because it's not only then 2 entities, but you have the different combination of the route choice, because the people from the suburb can choose the on-ramp, the freeway, or going through the perimeter control. So a dynamic trip route choice was also integrated in terms of the modeling. And the control contribution was to provide first a system optimum approach for that. So it's a very big problem, lots of states and control parameters, but we were able, by waiting a lot of time, to get the system optimum by also optimizing the route choice, the behavior of the vehicle. So this is the upper maximum that we can get for this specific example. MPC was the centralized controller, and at the end we showed that there should be a cooperative decentralized MPC that is, of course, a little worse than the MPC, but it's efficient. So we were able to break down the large scale problem to two smaller controllers and provide the coordination among them. And in the decentralized MPC, as you see, the system goes to infinity because there is no enough coordination among them. So I couldn't resist to show a little bit of a math. So this is the final structure of the control that we are, as a tool that we are proposing for urban control system. So imagine it's big city, let's say Melbourne, and we want to control that. So in an MPC framework, we will use a plant, which can be a micro simulation, a real world, or in this case, we divide the city to 19 smaller suburbs. And for the optimization plan, we have the big picture for the first cornerstone of the perimeter flow control. And here, the control design from the MPC will go to a lower level feedback heterogeneity controller to provide provide local information in terms of the transfer flow between every two small subregions. And to provide some results, here is the three examples of no control, high-level controller, and the hierarchical, the final solution that we provided. So this is the example of the 19 subregions, the similar situation, similar demand, and the blue means the subregion is working fine, but the red means that the system is very congested. And everything is similar. So let's see what will be the results. So at the beginning of the traffic set, which is the rush hour from the suburb to the city center, you will see with no control case, the city center will get very congested. With the high-level controller, we have a heterogeneity over the system, but the hierarchical solution gets very fast to the uncongested regime. So that was it, and I would like to take this opportunity to thank Brendan and Javier for making this award happen, because it was very short time for me to come here. I would like to thank my supervisor, our team, our great team in EPFL, Lutz, and that's all. Thank you for listening.
If there are any questions, we can do that. If not, okay, well, thank you again, and congratulations on your award.
Thank you.
So we have one final award presentation before we finish this session, and this will be for the IEEE ITS Best Application Award, and presented by Fei Yu Wang from his work in Qingdao.
Thanks, Brandon. I come here on the behalf of my whole team, which is the picture of all of them. This is actually a project almost 20 years. And for Qingdao project, this is the main participant. It's from actually 7 institutes: the Qingdao Academy of Intelligent Industry, Qingdao Public Safety Bureau, the CASIA, Hisense, National University of Defense Technology, and the Tsinghua universities. So I will first give a brief of the project and then some of our future activity, and I'd like to get our society involved in the future. So this is a project phase 1 completed 2 years ago, which is the largest ITS project in China, financed by Qingdao Metropolitan Government. And it has many years. First city-wide application of a parallel transportation system, which is actually championed here in our society. And we have a graduate over 50 students, a PhD student, and we produced 2 national ITS stands and 30 patents and over 100 publications in these areas. So this is the main participants of the institute, main institute for this project. This is the effect actually over the city for the last year, which is the parallel means real and virtual together, as we call co-design, co-simulation, co-optimization, and co-control. So we finished because in China, all the performance of your system have to be certified by government. The certification was over last year, end of last year. And it's also very interesting to public because this first time show you have artificial transportation system, co-operate, optimize with the real one. So it's now become a project for scientific educations. And this is one of the report in the China national TV. And technically, this is all we have. We have this system for over 10 years. We have a real and a virtual work together. Is one more step from computer simulation to computational experiment. So the system now have 4 major parts at the center management side. One is ITOP, Integrated Transportation Operating Platforms, which run in the real and the virtual system. And then for management and control, we have ADAPS. And for experiment and evaluation, we have Dianni. And then for learning and training, we have OTST, which is operate training system for transportation. And then on field, now we control, for this phase 1, only less than 400 traffic intersection controller, over 1,000 traffic information collector. And then we have less than 200 VMS, and then video monitor and so on. And the nice thing is we also introduced the social medium into the pictures for WeChat and all the apps. And this is how it's running. We have a real one, we have artificial one, and connected through network is agent-based, and some of I also use cloud computing. The artificial transportation system for this project, we have over 1,000 sites, include residential area, official building, and schools, and so on. So this, we insert the population. Actually, for this one, the population we have is less than 1 million people. So in this way, the computer become a transportation labs. So you can create your own traffic accident. You can have like a game you can play. You have a big social gathering, and you evaluate the impact of those social event, and then evaluate your measurement to manage them. For control, we use, you can call this actually traffic robot, software robot, or you call agent. And we distribute all those agents over the networks. And all the thing I organize as a 3-layer: organization, coordination, and executions. So for this, we develop our own agent-based traffic controller instead of algorithm-based traffic controller. We developed this over quite a few years. Now it's 5th generations. And the result in Qingdao is very, very significant over the 2-year period in the evaluations. So it's like the number of vehicles stopped at the main street reduced 20 to 45%, and the congestion miles for major key road, especially that road called the Shandong Road, reduced almost 50%. So this is the result. And then the prediction is much better. It's 20% better than the old method using floating vehicles. So, and the social media. So now we can, for WeChat, we have our own network to distribute information. For less than a year, we already have 85,000 people registered to use this. And the time, the access time is over 14 million. So this is the social transportation part we introduced in this project. So this is this is part of the project, and I want to look at how we come to this stage. And this is George Soridis, my PhD advisor. He started apply intelligent control to traffic in the 70s. So I'm glad to let you know that the board of this society has accepted our proposal to rename the best regular paper. For the transaction, we have 2 best paper. One is the best regular paper, one is the best survey paper. So for the best regular paper, starting next year, will be renamed to the George Soridis Best Paper Award for the transaction, just in honor his 10th anniversary of his death 10 years ago. And this is what I find on the internet, some of his early papers in applying intelligent control to transportations. So this is why 3 of us, actually plus Yaobin Chen, made a proposal for the change. Petros, our new EIC for the transaction, told me George was the first Greek American professor he met at the CDC in 1881. And then George wrote the chapter for first cyclopedia of traffic control and the transportation system for Marcos. So it's all coming together. And I'm glad that we have this opportunity to honor the true pioneer for intelligent control from a control side. Actually, George was also the founding president of IEEE Robotics and Automation Society. That society has a George Soridis Leadership Award, and now our society has this Best Paper Award for him. I'm very glad of that. And the history of the parallel transportation system is, so before 1999, I always follow George's 3 level of hierarchical intelligent control for transportation. And this is why in Arizona, we have roaders, we have millers. But then I think there's some shortage of doing that, especially for complex system. Later in 1990s, few professors, actually 2 professors from anthropology department worked with me. We started research in artificial society. And then the Arizona started this PARCS, Program for Advanced Research in Complex System. I would become the first director. So I decided maybe there's good way of modeling complex system. And then we work with the Scientific Institute on this approach. Then China is applying for Olympic 2008. And our proposal is to use this new method for Olympic transportation system. So we made a proposal. Then actually in 2001 in Spain, a small city near Barcelona, the US department every 2 years has this workshop for next generation simulation. So I was invited to, it's the first time I come to Europe. So we made a presentation on that workshop, but it's only a discussion of idea. And then the 2001, 2003, we have another workshop every 2 years in Sedona, Arizona. I also made a talk about this, parallel transportation. And I remember half of people said, this is a crazy idea. I thought they are from engineering side, but it's turned out that people from universities think this is impossible, but then people from the state DOT think this is a good idea. I was really shocked about that. So then we wrote our first paper toward intelligent transportation system for 2000 Olympics. At that time, we are thinking we want to try this approach for Olympics. But in the end, they don't use this. And one of my course, who is in charge of the 2008 Olympic transportation system, but he's now in jail for the corruption charges. So I'm glad that we are not doing that part with them. And then we wrote our first paper on the ECP-based control method in 2004. Actually, I wrote the first paper on the parallel system for transportation is 2004 in Parma. And then lost my computer at the Milan. My whole luggage was stored. And it took me 5 years to recover that part. So the first paper on the transportation was published actually in the 2010. So this is a long history. But at that time, I think theory is not important. Let's do it. So we built our first system in 2006, pack all the computer and the traffic controller together. So, because I think if you use just a few computers to control traffic of a whole system, that's impossible. So you need to use a lot of computers. And then the 2008, this is the demo system we have at our ITSC, when ITSC was held in Beijing. But before that, it's only research experiment, no real use. The real use come in 2009 with a small city in Taichung, in Suzhou. The reason I select this city because 400 years ago, Zhenghe started sailing of ocean from that city. That was a small harbor. We only have 4 traffic controllers to control, but that's our first applications. And then the big application was 2010, used for the Asian game, but that time is not for urban traffic, it's only to control the public bus and the taxis. So, and that was the history. Look forward, and before I come to this meeting, we just had an agreement with the Qingdao Metropolitan Government. We will start the second phase next year with a budget double to the phase 1. So it's about 1.5 billion. And this one will include urban traffic, public transport, parking management, regional logistics, and social transportation. And in addition to that, there's 2 separate projects. One is the automated hub of Qingdao, which now is already number 6, 7 in the world. It's going to be, prediction is going to be number 7 in the world, going to be number 6 this year. And they will complete the automated part of the hub with a budget of alone has a 1.3 billion project. And then Qingdao will build a new international airport. And they allow, we can have a special road for automated vehicles, the smart vehicles. So which about 50 kilometers launch. I think this is going to be a very good opportunity for all the research, and I like everyone here in the society to participate. And we're going to, the government has agreed that to share all the traffic data with everyone, with the research, with us, and they're going to create a area called for entrepreneurship, for innovate, and for the so-called makers. And we already had started. This was the Joint International Center for Intelligent for Transportation Research when we have ITSC last year in Qingdao. And I hope this will not just a center in the paper, will be a real center and has a very close relationship with our society. And so the summer school we had this summer is just the first step. And I hope we're going to have we have our own office, and any of you are interested can go there and to do joint research and have the access to field evaluation, field experiment there. So, and in the future in this conference and also IW, we're going to like TRB, we're going to have a friend of QAI and state lab, so we can share the idea. And with that, we last month, China also created is Intelligent Vehicle Pooling Center, and I was a founding director. So we hope this will integrate our research in intelligent vehicle into the intelligent transportation systems. So this will be the IVPC. In terms of land, the real test site is like 3 times as big of MCT, and the construction is supposed to be completed before the IV 2008. So IV 2018 will be in this site, and I would like to welcome every one of you to be there. So I remember 10 years ago when we started this society, some other professional people from other professional society think our society will be a joke because we cannot do the real traffic. And now this year is our 10 years anniversary. What a great joke we have. I think we are all here, we enjoy our joke. Let's continue, let's do the transportation differently. Let's make sure the intelligent transportation system do have that big I, intelligence in the system, make our life better. Thank you.
All right, if there are any questions, we can ask now. Okay, well then let's thank Professor Wang again, and let's also thank all the award winners and all the speakers today. We are really proud of all of them, and again, I encourage you all to think about next year applying for some of these awards. And with that, I think we can close the session and we will have a break now. Thank you very much.